This is part 3 of Unit 2 of Quick Precalculus Review for Calculus. In part 1 of Unit 2 we were given a compound interest problem, and we solved the compound interest problem using this compound interest formula. In part 2 of Unit 2 we thought about the exact same problem and the exact same formula, but we thought about it in terms of functions. We took the r, the n, and the t to be fixed, and we thought then of this formula as defining the accumulated balance A as a function of the principal P. We also solved that formula for P as a function of A and thought about inverse functions, which is one of the main themes of Unit 2. In this video we'll continue thinking about the same example and continue thinking about inverse functions in much more detail. Operational, symbolic, numeric, and graphic relationships between inverse functions that hold in general, but we're going to think about them in the context of this example. And here is the example, labeled example 2.1. If you haven't solved this problem yet, you should pause the video and solve it on your own. We are now going to go down to the functions that we used in the last video to help us think about this in terms of functions. So first of all, we enter the values of r, n, and t. R is the nominal annual interest rate. It's 8%, which we type in as a 0.08. N is the number of compounding periods per year. Since it was quarterly compounding, n was 4. T is the number of years. You can see that these values are not entered yet because r, n, and t are blue. Once I do a shift return to enter these things, watch the r, n, and t will turn black, and you can confirm, for example, that t has been stored in Mathematicus memory as a value of 10. We need to enter the function next. A is a function of p. Again, r, n, and t are fixed numbers in Mathematicus memory, so they are showing up as black. P is the independent variable. It matches here and here. It's showing up as green. It doesn't have a stored value. Square brackets are function arguments. When you first define the function, you use an underscore, and I like using a colon equals. Watch though, the f will turn from blue to black once I enter this. 1, 2, 3, go. Yep, now it's black, and you can confirm that it is entered by typing f of p without an underscore and seeing that it is entered. Mathematica will approximate and simplify the formula for f of p here to this 2.20804 times p. If you check on your own, you can check that 1 plus r over n to the nt power for these values is 2.20804. Alright, that's a direct proportionality. A is directly proportional to p. We can plot this graph, the graph of this function. It'll be a straight line going through the origin. Before I go down to the graph, though, let me emphasize, as I've shown in other videos, that you can use the table command to plot specific points. Table creates lists in Mathematica. Lists are things sometimes containing numbers separated by a comma inside curvy braces, which is the kind of thing that you see here. Table in this case is going to create a list of sublists, a list of these kinds of things which I'm going to think of as being points when I use a command called listplot. P comma f of p, these are going to be points that are on the graph of f. This syntax specifies that p starts at 0 and goes up to 10,000 in increments of 1,000, so it's 0, then 1,000, then 2,000, etc. I'm going to store this list in a variable I'm calling f points. Notice f points is blue here initially, but now when I enter it, it turns black, and I can confirm by typing f points and entering it that I get the exact same list. And you can test, for example, that when p is 2,000, what is f of p? It should be 4,016.08, and you can check on your own. If you multiply 2.20804 times 2,000, you will get that. So these are points that are on the graph of f. I can use a formatting command called table form to show the output in a nice way as a table like you might make by hand. Here are the values of p that I picked and the corresponding values of f of p, and these are the points that I can graph with listplot. Let's do the same kind of thing with the inverse function before we go ahead and look at the graphs. So here symbolically is the inverse function. Okay, here's the original function. A equals f of p equals this. Again, think of r, n, and t as fixed. I can divide both sides of that equation by 1 plus r over n to the nt power to get the inverse function right here. This notation is p equals f inverse of a. It's not f to the negative 1 power, it's f inverse of a. You do not want to swap the a and the p around here. That would be a bad idea because they have specific meanings, p being the principal and a being the accumulated balance. If you swap them, then the meaning would change. Do not swap them here. I can enter that function here as well. I can confirm it's entered. I'm typing it as f_inv. There it is. That number 0.45289 is the reciprocal. It's 1 divided by 2.20804. It's the reciprocal of that number. And since a is directly proportional to p, it should make sense then that p would be directly proportional to a. I can once again use table and table form to make a table of values of this function, the inverse function, though you'll notice that I'm specifying how the values of a are going to change in kind of a strange way. I'm starting at 0 and then going up to 22,080.4 in increments of 2,208.04. Why am I doing that? Why am I doing that? Well, look at this table and that might give you a hint as to why I'm doing it. If you recall, hopefully you remember that the points for the inverse function are obtained by swapping the coordinates of the points of the original function. And so that's what I've done here. This table consists of points that are swapped. The coordinates are swapped from this original table of the graph of f. Alright, then I can go ahead and graph these things. I've added a lot of graphs of options to the graph that I made in the last video to show these graphs at once, and in particular I want to point out that I'm using list plot right here, for example, to plot the points f points, and list plot again to plot f in points right down here. I'm combining them with show and grid, and I get this picture right here. I've made the axes scaled the same, and we can see it does seem like perhaps these are reflections of each other across the line y equals x, but be careful, you really shouldn't think of that too specifically in this example because a and p have specific meanings. So in reality, you really should graph these on two separate sets of axes labeled differently if you are always treating the horizontal axis as the independent variable. Okay, but the graphs are indeed related to each other. So that's a graphical illustration of the relationship between them. What happens symbolically and operationally? Let's go back up here. Here's a question. What happens when we plug one function into the other? Or in other words, when we apply one function right after the other? When I write this symbolism right here, f, what you should say is f of f inverse of a, I am plugging f inverse of a into the function f. Alright, so what we can do to solve for this and see what it equals initially, for example, is we can replace f inverse of a with the formula for f inverse of a. Either one of these is okay. I think I'll replace it with a fraction this time. So I'm replacing, in the formula for f, what this means is I'm replacing p with this expression, this fraction. Wherever I see a p over here, I replace it with this expression. So let's go ahead and do that. That expression, that fraction, is going in place of the p right here, but don't forget then to multiply it by this thing. It's not letting me highlight just the 1 plus r over n to the nt power by itself. Get rid of the p here. This is representing p. This is p times this thing when I plug in this value for p. But obviously, now we get a division out of these expressions. This simplifies down to a. So f of n, f inverse of a equals a. Operationally, what's happening? When you plug a, an accumulated balance, into f inverse, you get the corresponding present value, which is denoted f inverse of a. But it is a value of p. Then we take that number and plug it back into f to find the corresponding accumulated balance. It should make good operational sense that we get back to the original accumulated balance as well. We can do a similar kind of thing with in the opposite order. We can type the inverse function, f inverse of f of p. So we plug in the formula for f of p into that expression. The formula for f of p is right here. And what this means is we plug that expression into the formula for f inverse now, in place of the a. So wherever I see an a, whether I use this form or this form, I replace it with this expression. Okay, so I think I'll go ahead and use this part, that formula. I'll replace the a with this expression right here. And once again, you get simplification. The 1 plus r over n to the nt powers divide out, leaving you with a p. So once again, you get a nice operational relationship that if you plug in a principal into the formula for f to get an accumulated balance, and f of p, an a value, and then you plug that back into the inverse function, it undoes it, it gets you back to the original principle. Mathematica can confirm this as well. If I type f of f inverse of a and enter that, it comes back as 1.1 decimal times a. Okay, that means 1 times a, that means a. Okay, it's because of the Mathematica's way of dealing with decimals that you see the 1 decimal here. Just think of this as an a. If I do it the other way around, if I plug f into f inverse, I also get probably 1 decimal times p in this case, which just means p. Okay, 1 times p. This is just a p. So this is Mathematica's way of confirming these equations. But I want to emphasize as a lesson here, so to speak, is that these equations work. These are symbolic relationships between functions and their inverse that work no matter what kind of function you have. The fact that f of f inverse of a equals a for all a in the domain of f inverse, and f inverse of f of p equals p for all p in the domain of f, is the symbolic relationship that always holds between inverse functions. There's a graphical relationship that I already showed you. I'm going to end this video by showing you that graphical relationship in kind of a nice way. We talked about reflecting across the line y equals x, though, and again in the context of the application, you shouldn't think of it that way. Down here I've got essentially the same functions, generic forms of these functions, entered into Mathematica with this Mathematica code that you see right here. That's going to allow me to see that nice graphical relationship in terms of a reflection across the line y equals x. So we're not thinking about the real life meaning of the numbers this time. Here we have the line y equals x in this dashed green. This red line with the black dots is the graph of f. And the blue line is the graph of f inverse. And here's a nice graphical way to see the reflection property. If you draw lines that are perpendicular to the green line from points in the graph of f to the graph of f inverse, this is illustrating how they are reflections of each other across this line y equals x. But again, you should only think about this in the context of where the functions don't, the variables don't have any real life meaning. And I'll end the video there.